Thank you for joining the Once Changing the World, India's first Future Tech Meets Sustainability podcast. And today I'm delighted and honored to have with me Dr. Mike Curtis, who is the president and CEO at eGenesis, and he's responsible for managing the development of eGenesis Xenotransplantation programs. Dr. Curtis was featured on Time magazine list of 100 individuals who influenced global health this year. He has more than 25 years of experience in scientific research and leadership in biopharmaceutical drug development across multiple therapeutic areas. Before joining eGenesis, he served as president and head of R&D at Cadent Therapeutics. Prior to Cadent, he was with Catabasis Pharmaceuticals and Infinity Pharmaceuticals, where he established and led a 30-member scientist team that was responsible for all product development activities, including the advancement of the lead candidates into phase 3 clinical trials. Dr. Curtis holds an ASc in Biotechnology from Cobleskill College and a BSc in Biochemistry from the College of Environmental Science and Forestry. He earned a PhD in Cell and Molecular Biology from the State University of New York Upstate Medical College. So, Doctor, really appreciate you taking time and being part of the podcast. The topic today is going to be xenotransplantation and the future of organ donation. It'll be great if you can start by explaining the challenges of organ donation, right from the organ shortage to the current duration our organ can be preserved before a transplant.
Yeah, great. And thanks, Eddie, for having me on. It's great to be here. And then we also, as the example, with regard to the unmet need. So, for instance, in kidney transplant in the United States, there's about 90,000 patients on the transplant wait list. And this wait list is in place because there's just not enough organs to supply everyone that needs an organ transplant. Therefore, we established an allocation system. In the United States, we can only do about 25,000 transplants a year because there's not enough organs available. So that leaves a huge gap. As patients spend more time on dialysis, they progressively get more ill. And many patients, about 50% of patients, die on dialysis. What's been missing is a renewable, scalable supply of transplantable organs. We know if we can find an organ for patients that they end up doing really well, the search for the past 40 years since the discovery of human-to-human transplant has been to find a renewable source of organs. And the field has investigated and really focused on the pig as the ideal donor to produce a renewable supply of transplantable organs. Kidney is one example. I think there's a huge unmet need in heart transplant. It's one of the leading causes of death in the world is heart failure. And then we also are working on a program to treat patients who are in acute liver failure. So we've shown over the previous decades that transplantation is a very effective treatment for patients with organ failure. We don't have enough organs to supply everyone that needs one. And this is where the idea of xenotransplantation comes in.
Organ shortage, I think it's a global issue. It's not just USA. In India, I think we've got somewhere around 500,000, the data I kind of checked, at least in 2021, 500,000 people who are on the waiting list. And the numbers are growing because, there's an acute shortage. Besides that, even the preservation techniques, from the time, when you kind of get an organ from a donor to, preserve it, it's normally just a couple of hours to maybe just maximum a day or two, so there are various problems. And yes, I think xenotransplantation, the approach is going to be completely revolutionize the organ transplant industry. Xenotransplantation, and not many people kind of are aware about what xenotransplantation is. So I think it'd be great if you can explain in layman's term what xenotransplantation is and how it works.
Yeah, so from really the beginning of modern medicine and the realization that people are passing away from organ failure, this idea of how do you replace or how do you treat people with that type of condition. Even in the early days of transplant, the idea was, well, could we use organs from animals to replace our own organs? So that's really what xenotransplantation is. It's what we call cross-species transplantation. So it's taking an organ from one animal and putting it into a person. In the early attempts at that, were not successful at all. And what researchers saw, or surgeons saw, was what we call hyperacute rejection. Right. So if I took a organ, let's say a kidney from a pig, without any changes to the pig, and tried to implant that into a monkey, it would be rejected in minutes to hours. So it's not effective. And so then it was realized that, well, we need to do something. If we want this to be successful, we need to do something to improve the compatibility between, in that case, porcine organs and human recipients. We did do many experiments with primates. So, one idea was, could we take organs from monkeys and transplant those into people? I think the outcomes were a little bit better, but they still were not sufficient, right? You still couldn't get multiple years of survival. So you would still likely have to improve compatibility. And I think the other challenge with cross-species transplantation from monkey to human is there's a much higher risk of what we call zoonosis, right? So the potential to transmit a disease from the donor animal, in this case the monkey, into a person is much higher because monkeys and humans are so closely related that diseases that can affect the monkeys often affect humans.
So, doctor, can you kind of explain this process? Can you just kind of step backward, and how does this creating a human compatible, genetically engineered organ works? I mean, can you talk about the rigor, the R&D, the testing gone behind this bold move, and how long did it take you from the idea stage to where these organs are grown now in animals and safe to be deployed in humans?
So when it was realized, 40, 50 years ago that we couldn't just take a porcine organ and put it into a person and it would work, that's when the research really started. And scientists were looking for, what is causing what we call acute rejection. So what are the factors that lead to acute rejection? What they found out was that there's carbohydrate differences or sugar differences between the animal donor and human recipient. And then the humans or monkeys would have antibodies against those carbohydrate differences. So the first order of business was to try to make the carbohydrates more similar in the animal donor to the human recipient. So there's probably about 10, 15 years of research to determine how to do that. And they identified those carbohydrate differences and were able to eliminate those from the pig genome. So once we did that, things improved, but they still weren't good enough. And so the next set of edits were really to introduce human regulatory genes to the pig genome. So one thing that can happen when we add a porcine organ to a person is a phenomenon called coagulopathy, right? So you'll get these small clots in the kidney, and that's due to coagulation incompatibility. So we introduce genes into the pig genome to address all of these mechanisms. In our donor, for instance, we introduced 7 regulatory transgenes to control coagulation and then the immune response. And then the last thing that was identified, and this was in the 90s, it was shown that every pig breed carries what we call retroviruses. And these are in the genome of every pig. And I think a parallel is HIV. HIV is a retrovirus. HIV crossed over from primates into humans. That's what the current data suggests. And so when this was discovered, and it was shown that those porcine retroviruses can infect human cells, it really slowed down the progress of xeno because nobody knew how to mitigate the risk of what we call retroviral transmission. So transmission of a virus from a pig into a potential human recipient. So at this point, this is probably 30 years in, right, we understand how to improve or reduce hyperacute rejection. We understand how to improve compatibility by introducing human transgenes. But the retroviral piece, we didn't have a good way to deal with, because in every pig genome, you're going to have 50 to 70 copies of these retroviruses. And they're scattered through the genome. And then about 12 years ago, along comes CRISPR-Cas9. And CRISPR-Cas9 is a revolution in the ability to edit the genome. Right? So it gives us a tool that allows us to go in and selectively edit nucleotides or bases, messages inside the genome. So in a pig genome of 3 billion bases, we need to go in and edit 57 of them. CRISPR is a tool that can allow us to do that. And that's what the company was founded on by George Church and Luhan Yang out of Harvard, showed that you could use CRISPR-Cas9 to create what we call inactivated retroviruses. So we go in and we use CRISPR to inactivate all 57 copies of the retrovirus. So this was about 7 years ago when that breakthrough happened. And so since then, we've been building a pig that includes all of this. So our donor that was used in the first ever human kidney transplant in a living person included 3 edits to control the carbohydrate compatibility, 7 to control long-term or promote long-term graft survival, and then 57 to, 59 to inactivate the retroviruses. So the donor that was used in the first transplant carries a total of 69 edits to the genome. So making that initial foresight donor took us about 5 years. And then about 2-3 years ago, we started to study that in monkeys. In this past fall, we published a paper in Nature summarizing 21 transplants in monkeys using the same type of kidney that was used with Mr. Slayman, and showed that we could get over 2 years of post-transplant survival in the monkey. That's what led us to performing that first transplant.
Right. So congratulations. I mean, for the world's first transplant, Mr. Slayman.
Yeah.
So 69 gene edits. How cool is that? And I think, CRISPR-Cas9 has completely revolutionized the approach of how we are looking at splicing and editing these genes, these genomes. Now, why just pigs? Because, I personally thought, these monkeys which had around 98.8% similar, genome, I thought monkeys would be like the ideal candidate, when we are kind of creating these human compatible organs. So why pigs? My first question. And what is eGenesis focusing on at this point in time? What are the organs that you are going after? Are there any blockers you think currently, or eventually do you think, you would be able to grow any kind of organs and any kind of tissues?
The closest related, non-human primate to human is the chimp, right? And so the chimp is actually a little bit smaller than a person. And so the organs aren't the right size. Ethically, we struggle studying chimps. We've actually banned chimp research pretty much across the world now. And so the smaller primates, things like baboons, and they're just too small. And then they also have the potential for the zoonotic risk, right, where they can introduce disease potentially into the human population. And then the last bit is engineering them, because they have relatively small litters, is really hard, right? So when you look for a species that's kind of the right size, so big enough, the organs need to be big enough, they need to be scalable, right? So we need to be able to make the animal at scale. Well, we already know in the world we make hundreds of millions of pigs a year in the agriculture industry. And then we need to be able to engineer and edit, right? And so when you add those kind of three major factors, you really get to the pig. And this is what's been shown again now for 30, 40 years, is the ability to engineer the genome, the ability to produce multiple piglets per litter, and then the ability to scale production is really why, and it seems to be working too. I mean, that's the other really important piece. But I think add that together, that's really why the pig has been chosen.
Right. And my second question was, which organs are eGenesis going after? And are there any blockers? I mean, eventually you think that you would be able to create any kind of organs, any kind of tissues? We started with, and the field really started with heart and kidney. And the reason is, one, that's really where the most need is, right? There are most people that are waiting for an organ transplant are waiting for a kidney or a heart. But they're also, from a transplant and compatibility perspective, relatively simple. Because the kidney is essentially a filter, right? Blood filter. The heart pumps blood. They do a few other things, but relatively minor. So the compatibility is pretty good to start with. Something like the liver, there's so much incompatibility between pig and human because the liver is basically a protein factory, right? So it's making lots of things that your body needs that if we put a pig liver in, it's making the pig version of that. So we would need to do a significant amount of editing to improve the tolerability of a liver. And then lung, for instance, is incredibly immunoreactive, right? So people have asthma, I have a cold, right? The lung is primed up to be rejected. So the lung is very challenging from a xenotransplantation perspective. So we start with the kidney, we start with the heart. We have a liver program, but instead of doing a transplant with a pig liver, we do what's called perfusion. So we have the liver sit outside the body on a perfusion pump, and then we perfuse the patient's blood through the pig liver. And we can do that. We've already shown in decedent subjects, we can do that for over 3 days. And what that does is that gives a patient who's in acute liver failure the opportunity to recover. And so those are the three major programs. One of the things I think the field of transplant has taught us over the past 50 years is never say never.
I mean, at the beginning of transplant, people thought transplanting organs from one person into another would never work, right? And the first few tries didn't go well, right? We had to figure out how to do it. And sure enough, over time, we figured it out, and now it's relatively routine. I think xenotransplantation is similar. It will have a similar arc, right? Where people say it's impossible, you'll never get there. And now here we are, I think with reasonable products that give patients a chance. So I think in the near term, we're going to see kidneys and hearts move into clinical trials and actually become available to patients. And I think it will be followed by those other organs, because we need to understand the compatibility of these porcine organs in people to then inform the engineering. The challenge with CRISPR is you can do anything, right? We can make any changes to the genome that we want to. And so the question is, well, what changes do we make next? We have this pig with 69 edits. We could make a pig with 100 edits. So there's really no theoretical limit to the amount of editing that we can do. The question then is just, what do you do next? And we think that the human data is super important to inform that engineering, because we've been optimizing for the monkey for 30 years. And there's only so much you can learn from monkey transplants. And I think now that we're in people, we're going to learn a lot more, and it's going to inform kind of what the next challenges are to get long-term survival of the organ. Because our ultimate goal is to produce organs that don't require suppression, right? And so if you, again, share the vision that someday we don't have to do human-to-human transplant anymore, it's all going to come from animals.
What a wonderful future would that be, because yes, globally we do have organ shortage, and you said, never say never, but the normal how people or the institutions react on something which is new or anything new, whether it's tech, is always it's in a very negative way. But over the years, everybody gets used to it, because who would have thought that you would have pacemakers and you have all of these tools which kind of augment us, even the glasses which kind of augments us, because without the glasses, I'm at least I'm like not able to see very clearly, and but I think through history, you have these tools and technologies which helps human to evolve. And I guess, we need to kind of go with the time, and yes, never say never, because I think we are constantly accelerating, and these tech and tools are accelerating in insane pace. And I'm sure with with genetics is going to meet AI and is going to converge, and the real world utility is going to be humongous. With CRISPR-Cas9, genetic editing tool, it's almost kind of changed the biological frontier, and researchers are pushing the boundary, with 3D printed tissues and organ. This is like a little futuristic question, but what are your thoughts on in the future? Would there be an organ which could be incubated, grown in an artificial environment, so that we kind of, we miss out the animals completely? We don't have to use an animal. What are your thoughts on something like that?
Yeah, no, I think it's, in theory, I think we can do it. Again, I think if you can go back to the, human-to-human transplant, now xenotransplant, no one thought we could do any of those things, right? And I think it's possible. I think there's still some gaps in our understanding of how, cells differentiate to make organs, right? And how we control that cell biology, but in the developmental biology, to take a stem cell and turn that into a fully functioning kidney, I think it's possible, right? It's just we don't exactly know how to do that yet. But with enough work effort, I think we can get there, right? But I think it's not in the near term, certainly. But I think it's theoretically possible. So I'll use my own phrase, never say never. Like I think the 3D printing, I think the stem cell derived approaches, there's some actually very interesting chimera approaches where you make basically a human liver inside of a pig or of a surrogate. So I think there's all these technologies that have the possibility to allow us to do things that we can't do in animals, right? Allow us to customize organs. There's this one dream of, if you needed a new kidney, I can take a stem cell from you and then make you a new kidney. And the science says it's possible, right? There's some gaps in our knowledge, but there's nothing to say we can't do it, right? There's no known barrier. We just have to figure it out. And again, that's one thing that mankind has shown over the years. We can figure things out.
Right. I think there's so many scientists around the world who's kind of pushing the boundaries. There's something called as organoids. You take these stem cells, turn it into a pluripotent stem cell, and then voila, you can kind of create any organs that you want. Though these are like minuscule organs, but eventually, I'm sure with the research in the next possibly decade, a couple of decades, you'll be able to, grow into these full-fledged organs from your cell. Can you talk about your clinical trial, the world's first successful transplant of your engineered
Yeah,
organ,
be happy
Richard
to.
Slayman, but he passed away, this month, and I believe
Yes, you did.
you and including the surgeons estimated that the pig kidney would last for 2 years. What went wrong, and what's been the learnings?
Filter, right? Blood filter, right? Blood. Yeah.
Xenotransplant.
Yeah, no, it's a great question. And, one, we're incredibly grateful for Rick and his family to go on this journey with us. Because one of the things to quickly realize is that this doesn't happen without patients, right? I mean, we can develop all the cool science in the world, but we need to develop products that can help patients. I mean, that's what our focus is. And you need patients like Rick to step up and agree to be the first. We're so grateful that he put his trust in us, with our pig kidney and the team at Mass General to do the surgery. And it was really, why we felt we were ready was based on the primate work that we have done over the past, 5 years, right? Where we were getting consistent long-term outcome in the monkey, right? So we have a data set that includes several animals over 600 days post-transplant, 7 animals over a year post-transplant. So we felt as though there wasn't more to do in the monkey, right? There's no more primate data that's going to make us feel comfortable going into patients. So it was time to go into patients. We've been in discussions with the FDA about starting a clinical study, which we're targeting to start middle of next year. And then last fall, here in the United States, the National Kidney Foundation had a patient advocacy meeting where they brought patients in that were at different stages of kidney failure, right? So patients who were the newly diagnosed, patients who've had a kidney transplant, patients who've had a failed kidney transplant and then find themselves back on dialysis. In the United States, if you look at the statistics, if you're over 50, you have a failed allo transplant. So you'd have a failed human-to-human transplant, and you find yourself back on dialysis. You are at very low odds of getting a second transplanted kidney, right? So you're going to spend the rest of your life on dialysis, and you're likely going to pass away on dialysis. And so when you talk to those patients, they're looking for options, right? And so we have this porcine kidney option. Now, in Rick's case, he was also losing access to dialysis. So at some point, he would no longer be able to receive dialysis. So in the absence of a living donor kidney transplant, Rick was going to pass away. So when we talked to the MGH nephrologists, and they knew what we were doing in kidney transplant, they were like, should we try? And so we had looked at maybe 4 or 5 other patients that might be good candidates. And so Rick's nephrologist approached him with this idea, and laid out the possibility, the risk and the benefit, right? It could work, it may not work. Now, Rick also had a significant cardiovascular risk, right? So he also had some heart conditions. But overall, he was a very relatively healthy guy and was a good candidate for transplant. So after many weeks of talking to Rick about the risks and consenting, we took it to the FDA and laid out why we thought this was a good thing to do for Rick, and the FDA agreed. And so I think when you look inside the world of end-stage renal disease and dialysis and transplant, you can find patients like Rick who have reached the end of the treatment options and will find themselves approaching the end of their life. And porcine kidney transplant gives them a potential hope. So when we did the transplant on March 16th, it was a huge step, obviously, forward for the field, for Rick, for us, for everyone. And again, just to emphasize, we view Rick as integral to advancing this technology as any of the CRISPR stuff we've done, or any, he has as big a role as any of that stuff, probably bigger. And it went incredibly well. On day of so he had not produced urine on his own in over a year because he was in kidney failure. He was on dialysis 3 times a week, 4 hours at a time. And then on the first day of the transplant, he was making urine on his own. His creatinine pre-transplant, which is a measure of kidney function, had gone from 10 to down to 1.5, which is more or less normal. So the kidney functioned great. I think he was feeling well. He went home 18 days post-transplant, and things were looking good. We were really excited about the progress. I think he was excited about the progress. And then on day 51, Rick had come into the hospital in the morning for a checkup, and the kidney was looking good. But then that evening, Rick was found unconscious, and Rick passed away due to a cardiovascular event. So not the outcome we clearly wanted for Rick, but it's a reminder that in this patient population, these patients that have struggled with ESRD for a long time have other what we call comorbidities that we have to be able to manage and deal with, right? So he did have a relatively high cardiovascular risk, and so that's what ended up leading to his passing away.
Right. What was the learnings from that trial? And are there any other clinical trials besides your team that's vested in xenotransplantation? And what's been the track record so far?
I'll start with that. The learnings are tremendous. One is the immunosuppression regimen that we used in Rick's transplant was the same regimen that we used in the primate studies, and it seems to work really well. Right, so the kidney was performing, well after 51 days post-transplant, and Rick seemed to tolerate the immunosuppression pretty well. And the kidney functioned, robustly. So that is a huge first step. There was no guarantee that was actually going to happen. And so one of the things this taught us is, should we actually study this next transplant in maybe a patient with a little bit less cardiovascular risk? But it emboldens us to go try again. Right, because the kidney itself functioned beautifully, right? Which is, patients with that end-stage renal disease, that was the first challenge, right? Once their kidneys fail and they can't get dialysis, they're going to pass away from kidney failure. So it went about as good, at least in the first 51 days, as we could hope from a kidney function perspective. And again, not the outcome we wanted for Rick at all, but it taught us that we know enough, we believe, and we're going to go back to the agency to talk about it, to go again. So one thing that inspired us to propose this first transplant to Rick was about in the past couple of years, there were 2 heart transplants done in living patients at the University of Maryland. Mohammed Muad'Din and Bart Griffith performed what we call the Bennett and the Fawcett transplant. So these were 2 porcine heart transplants that were completed in patients that were suffering from end-stage heart failure. Now, these are older gentlemen who were hospitalized. They had really no chance of getting a human heart transplant. They couldn't stay on supportive care much longer, so they were reaching the end of their life. And Mohammed and Bart did those 2 transplants with some success. The hearts function for 40 and 50 days, and unfortunately, when those hearts fail, those patients pass away. So that to us was a little bit of an inspiration to say we should try a kidney transplant in patients that are kind of reaching the end of the treatment options. Now, 2 other groups have been studying kidney transplant in what we call decedents. These are patients who are in brain death, who might otherwise be an organ donor, but for some reason are disqualified from organ donation, so they donate their body to the study. And Jamie Locke at UAB and Bob Montgomery at NYU have done kidney transplants in these patients, and Bob has done some heart transplants. And those were important steps to show that we don't see hyperacute rejection with the editing that we're doing in the pig. And then shortly after we performed the transplant with Mr. Slayman, Bob and the team at NYU performed a kidney transplant in Lisa Pisano. Lisa was suffering from heart failure and kidney failure. So Bob and the team installed a ventricular support device to support her heart. And then a week or so later, did the kidney transplant. As far as we can tell from the last we heard, Lisa's doing well. And I think it's another big step forward for the field.
Right, right. So again, I think congratulations are due, because I think you guys have gone down in history, because I think in another maybe a few decades, when this becomes like a normal, healthcare routine, in the organ shortage space, I mean, you guys will be completely celebrated, and so will be Rick Slayman for the role that he has played. How do you think this technology can be made accessible to patients worldwide? Considering obviously the cost behind something like
Yeah.
this.
Yeah, I think when we think of cost and you look at the cost of care for a patient with end-stage renal disease and on chronic dialysis, there's already a massive cost to the healthcare system where these patients are being treated. Last fall, we started to branch outside the United States. So we have a collaboration in Japan with a company called Pormatech. Because we make all of our donors by cloning currently, we can send cells to different geographies. And then if the teams know how to clone, we can turn those cells into donor animals. And so this past February, we had our first litter of eGenesis donors in Japan. And so I think if you use that as a model, we can move donor production around the world using cloning. So I think the intention would be to regionally produce animals for transplant. So I think the beauty of this approach is it allows us not only to scale, for instance, inside the United States, but it does allow us to scale around the world.
You were mentioning, I mean, in your engineered model, there was 69 edits of the gene. You said, there is no boundary as such. You could do 100, you could go beyond or more, right? So, do you think that these xenotransplantation would lead to the creation of designer organs with improved functionality, where you kind of augment it, go beyond?
No, it's conceptually possible, and I think there was some vision here of making quote super organs, and I think the challenge is right now we don't know enough to do that right now. Like, what would you actually do to make a super kidney? But it does allow us to augment any of the organs to try to introduce properties that we might want, right? So yes, I think you can start to go beyond just compatibility and start to engineer in traits or that may be desired in organs. I mean, some of the things we're talking about are, can you make kidneys that are refractory to disease, right? So for instance, there's some viruses that infect kidneys. Well, can we make a kidney that the virus can infect, right? So I do think there are this idea of augmentation. It's in the list. Candidly, it's very low on our list, but conceptually it's possible.
What are the biggest challenges remaining in making xenotransplantation a routine medical procedure?
Yeah. I think it's our goal really is to keep going into the clinic and collecting more data. 1 or 2 patients is a huge start, but we clearly need to study this in more patients, and we need to run controlled trials. But I think all of that is in the plan, and if it works as we hope it does, which I think these first generation organs, I'll give you an example for kidney. We think success is something north of 3 years, right? And I think from the primate data, I think we have the chance to get there. And if we do, I think that's the first generation product. And then what that will allow us to do is iterate, right, and engineer the animal in a way to promote longer term graft survival. So I can see in the next 5-6 years that we could bring that first product to commercialization, in patients like Mr. Slayman who are reaching the end of their treatment options. I think that's our initial target population. And then from that, we can build, right? And we can go into a much broader population. So I think we, again, assuming we continue to get good data and we see good outcomes, in the next 5-6 years, I think we could see the first products for kidney. I think for liver, it could be in the next 2 or 3 years, because the unmet need in liver is even more dire, because there is no dialysis for patients in liver failure. That if we can improve the outcomes for patients in liver failure, those endpoints are relatively short. Right? We're looking for improvements in survival in 30 days versus 3 years. And so I think we can move a little more quickly in those clinical studies.
What's your moonshot? What's the future vision of eGenesis? Where do you see eGenesis in the field of xenotransplantation in the next 5 or 10 years?
Yeah, so for us, in the next 5 years, it's to have 3 products available for patients. Kidney transplant, liver perfusion, and then pediatric heart transplant. That's it. I mean, that's what we're laser focused on, are those 3, getting those 3 programs to patients. Because we believe that we have products right now, that can extend patients' lives.
Right. Doctor, really, really appreciate you taking time being part of the podcast. More power to you and the entire team at eGenesis. I think we're sitting at a fantastic point in time where we are kind of completely relooking at how healthcare can be done, and organ shortage. It's such a huge problem. I really hope and I wish and I pray for a world that in the next couple of years we get to the world where nobody's got to wait for any organ. So really, really appreciate you taking time and being part of the podcast. And to my listeners, if you like what you see in here, then please press the subscribe button. Until next time, see you guys. Thank you, doctor. Really appreciate this.
Thank you, Eddie.